Hey guys, welcome back. We are looking at 6.1 today, which is talking about Riemann sums. So before we get started, we are going to do a quick little review. So in this review, we are going to look at how to find the area of some of these shapes. So if I have a square right here, to find the area, I'm just going to do 3 times 3, which gives me 9 centimeters squared. For this rectangle, I would just do the length times the width. So I'd do 6 times 4, which would give me 24 centimeters squared. But then when we're looking at a shape like this, we've kind of got to do a composition. So I'm going to do a line right here. So I'm going to look at this big rectangle and then this small rectangle. So the big rectangle would be 5 times 9. And the small rectangle is going to be this 3 times 1. So I can add them together. 5 times 9 is 45, plus 3 times 1, which is 3, and 45 plus 3 gets me my 48 centimeters squared. So these are shapes that we're used to looking at. What we're going to look at today is if we were trying to find the area under a curve, and we're going to use rectangles to help us estimate that area, approximate that area. So you can kind of see in this picture already, it shows you how we are going to be using rectangles to kind of estimate the area under the curve. So what we're doing right here is called a right sum, a right Riemann sum, because we are using the right endpoints for our rectangles over here. And so what I'm going to do is I'm going to take the area of all these rectangles and add them together. So this first rectangle is from 0 to 2/5, so I'm going to do 2/5 times our height, which if we're looking at our curve, our height would just be f of 2/5. So a negative 2/5 squared plus 5, and when you simplify that down, you end up with 121 over 25. So the area for this first rectangle right here is going to be my 2/5 times my 121 over 25. And now let's find the area of our second rectangle right here. So from 2/5 to 4/5, once again, it's 2/5. And to find my height, I need to find f of, instead of 2/5, now I'm looking at this right endpoint, which is 4/5. So that's going to be my negative 4/5 squared plus 5, which when you simplify that down in your calculator, that's going to give you 109 over 25. So my next rectangle is going to be 2/5 for my width right here, and then the height is my 109 over 25. And now let's look at our next rectangle. So this one, once again, we have that same width of 2/5. And to find my height, I need to figure out what is f of, and this time what I'm using is 6/5. And so when you do that and plug it into your calculator, f of 6/5 ends up being 89 over 25. So I'm going to do 2/5 times 89 over 25. And so that's going to give me the area for this rectangle right here. So now let's look at our next rectangle. We're going from 6/5 to 8/5, which once again is 2/5. And then I need to find my height. So the endpoint that I'm using is that 8/5. So I need to find f of 8/5. So if I have 8 over 5 and I plug that into my f of x equation right here, what I'm going to end up with is 61 over 25. So my next rectangle that I'm going to add to this sum of approximating the area of rectangles is going to be 2/5 times 61 over 25. And then we need to find our last rectangle right here. So my width is from 8/5 to 10/5, so 2/5 again. And to find my height, I need to find f of 10 over 5, which really is just f of 2. 10 over 5 is 2. And so when I plug that in, I end up with a negative 2 squared plus 5, and that's going to give me 1. So I'm going to have my width of 2/5 times my height of 1. So to estimate this area, I'm just going to add all those rectangles together, which we can do in our calculator. We're just taking this whole equation right here adding that all together, and you should end up with 162 over 25, which would be approximately 6.48. So that would be the area under the curve, and we are estimating this. So let's look at another one. This says use the process you used in number 4, the problem we just did, to estimate the area bounded by the curve. F of x is equal to x squared, so our parabola right here. The x-axis and the lines x equals 0 and x equals 2. So it's the shaded area right here. So when I do this, I am going to create a bunch of rectangles to kind of figure out what that area is going to be. And the more rectangles we have, the more accurate it's going to be. So I'm going to do 4 rectangles here, and so I'm going to use my 0.5 and my 1.5. So I'm also going to use my right Riemann sums. So that's going to come over and it's going to come down to my 1.5. Then I'm going to use the 1.5 point and bring it down to 1, and then this point here and bring it down, and then this point here and bring it down. So this time when I do right Riemann sums, it's a little bit different because here the rectangles were under the curve and here they're going to be over the curve. But we're still going to use it to kind of estimate what our area could be. So I am doing intervals that are each 0.5, so that means that my width for all of my rectangles is going to be 0.5. And now I just need to find my heights. So 1, 2, 3, 4 different heights that I'm going to find. So I need to find f of 0.5, f of 1, f of 1.5, and f of 2. So 0.5 squared gives me a 0.25. 1 squared is 1. 1.5 squared is 2.25. And 2 squared is 4. So for my first rectangle right here, I'll make this one red. My width is 0.5, so I'm going to do 0.5 times, and my height was here at 0.5, so it's going to be a 0.25. And then to find my next rectangle, we'll do this one in green. My width is still 0.5, and this time my height is there at 1. So now to find my third rectangle, so this rectangle right here, my width is still 0.5, and this time the height up here at this point is my 2.25. And to find my last rectangle, wrong color. Let's do this one in purple. This rectangle right here, my width is still 0.5, and my height this time is 4. And so now you'll notice that we have the same width for all of these. So technically I can kind of factor that out and do a 0.5 times 0.25 plus 1 plus 2.25 plus 4. So that could be a little bit easier for you when you plug it into the calculator, or if you do these by hand, plugging that in. Or doing all of that by hand, it makes it a little bit simpler. So we are going to use our calculator for this one since we have some decimals, and so if you plug this into your calculator or this multicolored one up here, you should end up with 3.75. So that's approximately the area under the curve. And notice I say approximately, we are estimating. And sometimes it'll ask you if it's an overestimate or an underestimate. So for this one, because our rectangles go over the curve, it's going to be an overestimate. And then this one, where our rectangles were under the curve, it would be an underestimate because we're missing parts of the curve there. So that's why this is an estimation. It's not perfect. It's not going to give us the exact area under the curve because we're using rectangles to try and estimate that. So for our next question right here, when it says what method are we using to approximate, we're using a bunch of rectangles and adding those areas together. And that is what's called a Riemann sum. So I'm going to type this out, and please forgive my bad typing. So this is called a Riemann sum. It is a method for estimating the area under a curve, or let's say instead of the area under a curve, the area bounded by a region using some geometric shapes, which in this case are rectangles. Rectangles. There we go. Like I've said multiple times, there is a reason that I am not an English teacher. So that's kind of an explanation of what we're doing here. So let's look at some more examples. And in these, we are going to compare a right Riemann sum and a left Riemann sum. So part A is going to find the right, part B is going to find the left, and we're going to compare which one's an over or under estimate. So let's do our right Riemann sums in, let's do purple. So a right Riemann sum is going to be in purple. So it says let f of x equal x squared plus x. Consider the region bounded by the graph of our f, the x-axis, and the line x equals 2. So it's going to stop over here at 2. We're going to divide it into 4 sub intervals that are going to be equal size, and I'm actually going to use our line drawing tool to help us out. So we're going to stop right here. So if I'm going from 0 to 2, I'm going to use my 0.5, 1, and 1.5 to kind of break it down into 4 equal sub intervals. So if I'm looking at a right Riemann sum, that means I'm using the right endpoint. So that means that my rectangle is going to come over here and then come down. Oop, I went a little too far. So it's going to come over and then come down, and come over and then come down, and come over this way and then come down, and then this one will come over right there. So that's what our right Riemann sum is going to look like. So what I need to do is I need to find the height at all of these points right here. And we know that our width is the same the entire time. It's 0.5 for all of these. So I'm going to start with a 0.5 out in front, and I'm not going to multiply it by every single rectangle because it's the exact same width. I'm just going to multiply it once. But I do need to find my heights. So we need to find f of 0.5, f of 1, f of 1.5, and f of 2. So 0.5 squared is 0.25, plus 0.5 is going to give me a 0.75. 1 squared is 1, plus 1 is going to give me 2. 1.5 squared plus 1.5 ends up giving me a 3.75, and 2 squared plus 2 gives me 6. So those are those points right there for my heights for my 4 rectangles, and so I'm just going to add those. I'm going to do a 0.75 plus 2 plus 3.75 plus 6. So that's going to be my Riemann sum for a right Riemann sum. And when I add all of those together, I end up with a 6.25. And we're going to say that this one is an overestimate because the rectangles go over the curve. So this is what we get when we do our right Riemann sums. Now let's look at our left Riemann sums. And I'm going to do our left Riemann sums in red. So my left Riemann sum means that instead of using these endpoints on the right, I'm going to use these points over here on the left. So when I do it this time, my curve, my rectangles are going to be under my curve. So this one is going to be our first rectangle. Then we've got our second rectangle here, cuts off here, and cuts off here. So we've kind of got these rectangles that are going under the curve. So we're using our left endpoints instead. So when I use my left endpoint, I still have some of the same values. Like I'm still going to use my 0.75, my 2, and my 3.75, but I'm not using this 6 right here. Instead, I'm using this point right here, which would be f of 0, and 0 squared plus 0 is just 0. So I'm still going to have the same width of 0.5. My first height is 0. Right here at 0.5, it's going to be a 0.75. At 1, we have the height of 2. And at 1.5, we have that height of 3.75. So we're still making rectangles, but this time instead of them being over the curve, they go under the curve here. So when I add all of this up, I end up with 3.25. And this one is an underestimate because the rectangles go under the curve. And as you can see, those numbers are pretty different. My 3.25 is very different from my 6.25. And so the reason for that is that we're using only 4 rectangles. If we used more rectangles that were smaller, our numbers would get closer together until we could find what that actual value would be. So let's look at another one. You jump out of an airplane. Before your parachute opens, you fall faster and faster, but your acceleration decreases as you fall because of air resistance. So the table below gives your acceleration in meters per second squared after t seconds. So graph the data below. So let's start by drawing our graph. At 0, we're at 9.81, which would be about right there. At 2, we're at 8.03, about right there. 4 is 6.53. 6 is 5.38. 8 is 4.41. And 10 is 3.61. So we've kind of got a curve coming down this way. So let me see if I can draw it and it doesn't look awful. That's not the worst curve. So that's kind of what we're looking at here. And we'll stop at that endpoint. Let's try this again. There we go. That's a little bit better. Okay, so it says use a left Riemann sum. So we're using a left Riemann sum with 5 subintervals of equal length and values from the table to approximate the velocity after 10 seconds. Show the computations that lead to your answer and use the correct units. So left Riemann sum and 5 subintervals. So if we're looking at 5 subintervals, let's go by 2s. 2, 4, 6, 8, and 10 gives us 1, 2, 3, 4, 5. And we're using left Riemann sums. So we're using these numbers that are going to make our rectangle go over our curve. Oh, that one should come from right there. So these are the rectangles that we're looking at here. And I know they're not drawn very well. Keep in mind, I can't actually see what I'm drawing on my tablet. So our width for all of these is 2. So I'm going to start with the 2 out in front, and then I'm going to use my height. So I'm going to use at 0, at 2, at 4, at 6, and at 8. So those are all coming from the table right here. So a 9.81 plus 8.03 plus 6.53 plus 4.41. So once again, since we have decimals, we can use our calculator. to help us get an answer here. And so our answer would end up being 68.32. And it does say use correct units, and it says we're approximating the velocity. So our units for velocity would be meters per second. So that would be our answer for part A. And part B says, is your answer an over or underestimate for the velocity? So our rectangles are going over the curve, so it is going to be an overestimate. And when it says why, I'm going to say because the rectangles go over the curve. And then there is a part C down here that says use a right Riemann sum. Use a right Riemann sum instead for part 7a, and then is that one an over or underestimate? So now if we're using a right Riemann sum, that means that our rectangles are going to be under the graph. So now we're looking at the rectangles that are under our graph, which means it's going to be an underestimate. But now we're also going to be using different points. We're using these right points, which means that instead of using our point at 0, we're going to start at our 2 right here and go to our 10. So our width is the same, it's still 2. And then I'm going to use all the points from 2 to 10. So 8.03, 6.53, and then it is 5.38, 4.41, and 3.61. Which also just reminds me, while I'm looking right here at this one, we actually skipped a point. So it's 9.81, 8.03, 6.53, and then right here, I forgot to write the 5.38. But that does give you that answer right there. I just forgot to add that in because we are having 1, 2, 3, 4, 5 subintervals, so we should have 5 numbers there. So 1, 2, 3, 4, 5, we've got all 5 numbers multiplying by our width. And so when we multiply that out in our calculator, we do end up with 55.92. Our units, once again, are going to be meters per second. And this is going to be an underestimate because the rectangles go under the curve. All right, we got a couple more questions that we're going to look at here. So our next number 8 right here, our next problem, this time we're not going to graph it, we're just going to go off of our table. So in order to determine the average temperature for the day, a meteorologist decides to record the temperature at 8 times during the day. She further decides that these recordings do not have to be equally spaced during the day because she does not need to make several readings during those periods when the temperature is not changing much, as well as not wanting to get up in the middle of the night. She decides to make one reading at some time during each of the intervals in the table below. So use a Riemann sum to find the average temperature for the day. So it's giving us our intervals here. So we need to figure out how many hours are in each interval. So from 12 to 5, that's 5 hours. From 5 to 7 is 2 hours. From 7 to 9 is 2 hours. 9 to 1 is 4 hours. 1 to 4 is 3 hours. 4 to 7 is 3 hours. 7 to 9 is 2 hours, and 9 to 12 is 3 hours. So those are going to be the widths that I'm going to use for each interval. And they're not equal this time, which means we can't just do what we've been doing by putting that same width at the beginning and then adding all the numbers together. We have to use the different widths for each interval. So I'm going to have 5 times my 42 degrees plus 2 times my 57 degrees plus 2 times my 72 degrees plus 4 times my 84 degrees, plus 3 times 89, plus 3 times 75, plus 2 times the 66 degrees, and plus 3 times the 52 degrees. So that's going to give us our Riemann sum. And you can plug that into your calculator or do it by hand, and you should end up with 1,584. But notice that it says find the average temperature for the day. So this is 1,584, and if we're talking about a day, we need to divide that by the 24 hours in the day to find that average temperature. So 1,584 divided by our 24 hours in a day is going to give us an average of 66 degrees. So that's kind of how Riemann sums and averages work together. It kind of makes sense based off of what you know about averages already. You're just kind of taking, okay, so it's 42 degrees in that 5-hour interval, so I'm going to do 42 times 5, and then kind of add it all up, and you end up with this big number, and then divide it by the number of hours in the day, and you get 66 degrees. All right. Number 9. So these are some more left and right Riemann sums. So we have our function x squared plus 1, and it says estimate the area bounded by the graph of the curve and the x-axis on 0 to 2 by using a left Riemann sum with 4 equal subintervals. So let's first start by sketching our curve. It's x squared plus 1, so we're going to start right here. 1 squared plus 1 gives me our 2. And 2 squared plus 1 gives me 5. So we do need 4 equal subintervals, which means I'm going to have to break it down even more. And I'm going to have to use a width of 0.5. So let's go ahead and find what 0.5 squared plus 1 is. So 0.5 squared is 0.25 plus 1 gives me a 1.25 right here. And then if I did 1.5 squared plus 1, that's going to give me 3.25. Should be right here. So we can connect those dots, and it gives us this half of a parabola right here. And we are using a left Riemann sum, which means that our rectangles are going to go from our left endpoints over. Oh. So from the left points over. So we get these rectangles here that go under our curve. So we've got 1, 2, 3, and then 4 right there. And so we're also going to be using these heights from our left points. So at 0, our height is at 1, and then we go to 1.25, then 2, and then 3.25. Our width is the same, so we can pull it out in front, and then just add all those heights together. So 1 plus 1.25 plus 2 plus 3.25. And so when I add all of that together and then multiply it by my 0.5, I end up with 3.75. And this one is an underestimate because the rectangles are under the curve. And let's look at B here. It's the exact same curve, so I'm going to go ahead and put my points back. I have 1 at 0.5, we're at 1.25, 1 gives me 2, 1.5 is 3.25, and 2 gives me 5. So we've got the same kind of half a parabola here. Pardon my really bad drawings. But this time we are using a right Riemann sum. So what that means is that I'm going to use my right endpoints. So it's going to come over our curve. So that is what our rectangle is going to look like this time. And I'm using my right endpoints, so I'm going to start up here with that 5. Then I have a 3.25. That one's at 2, and this one is at 1.25. The width for all 4 is 0.5, so I'm going to bring that out in front. And then I'm going to use my 1.25, my 2, my 3.25, and my 5. So once I add all those together and multiply them by my 0.5 out here, I end up with 5.75. And because our rectangles are going over our curve, this is going to be an overestimate. So an overestimate because the rectangles go over the curve. Okay, so the next little part says the exact answer for this one is represented by the integral. So this right here is called an integral. And this one is a definite integral because we're going from our interval from 0 to 2, and we're looking at our function x squared plus 1. So that's what this graph is right here, and that's what this graph is right here. So we did an overestimate and an underestimate, but we can find the exact area by using this integral right here. And we actually can do it in our calculator. So let's give my calculator a second to open up, and I will show you how to do that. So we are going to hit the math button, and then you're going to scroll down to option 9. So we talked about option 8, that can find the derivative at a point. We use that during optimization, but you also can just use it on your normal calculation screen. And so number 9 is going to find our definite integral. Fn is finite integral. So we're going to hit enter for option 9. We are going from 0 to 2, that's our interval. And the function that we were looking at was x squared plus 1. And then we need to put a dx out here because our variable that we're using is an x, so we need to put that out there so that our calculator knows that we're talking about x being the variable. And then if you just hit enter, it pops out your answer for you. I don't like that decimal, so I'm going to hit math, enter, enter, and it's going to give me my fraction, 14 over 3. So, it was 4.667 or 14 over 3. And so if we look at our Riemann sums and it says which one gave the best approximation, well, one was at 3.75 and one was at 5.75, so they both were kind of equally away from that 4.67. But it does look like the 3.75 would be a little bit closer, so our left Riemann sum, our underestimate, was a little bit more accurate. But they're still pretty far off from our actual value. And don't worry, we're going to talk a lot more about how to find integrals and find our actual area under the curve. But right now, we're just going to use Riemann sums to estimate it. So that was part C. And our last problem, number 10. A car is traveling so that its speed is never decreasing during a 12-second interval. The speed at various moments in time is listed in the table below. So part A says use 3 subintervals of equal length to estimate the distance traveled by the car during 12 seconds by using a left Riemann sum. So if I'm doing a left Riemann sum, that means I would use my left endpoints on the graph. But this one doesn't give us a graph. It gives us a table. So let's break this into our 3 sub-intervals of equal length. So if we're talking about 12, if I did 12 divided by 3, that would give me 4. So I'm going to go from 0 to 4, then from 4 to 8, and then from 8 to 12. So there are my 3 sub-intervals. And if I'm using a left Riemann sum, I'm going to use the left points for those 3 intervals. So the 0, 5, 421, and 845. So my width for all of these is that 4 that we just found right there. So I'm going to do 4 times, and then I'm going to do 5 plus 21 plus 45 for my left endpoints that I'm using here. So when I add that up and multiply it by 4, I end up with 284. And it says we're estimating the distance traveled by the car, and since we're talking about our speed being feet per second, our distance would just be feet. And then it says, is this an overestimate or an underestimate? So this one's a little bit harder to answer because we don't have a graph to look at. So let's actually look at part B, and then we'll come back and answer that question. So if I'm looking at part B, now we are doing the exact same thing with a right Riemann sum. So instead of using these left points, I'm going to use my right points, which would be the 21, the 45, and the 65. So my width is still 4, and then I'm going to do 21 plus 45 plus 65, using those right endpoints for the interval. So when I add all of that up and multiply it by 4, I end up with 524 feet. And so now that I have these 2 numbers, it's pretty easy to see this one's the smaller number and this one's the bigger number. So the smaller number is going to be the underestimate, and the bigger number would be the overestimate. So this one would be an underestimate because the rectangles go under the curve, and this one would be an overestimate because the rectangles go over the curve. So you can figure out which one's an overestimate and an underestimate without actually having a graph. If you're doing both of them, the smaller number is going to be the underestimate, the bigger number is going to be the overestimate. All right, that is it for this video. You guys do have some homework. That's 6.1 Go Formative. So make sure that you work on that, and you guys have a good day.